All right. So, so we basically, under some circumstances, this wire that we're transmitting over, like, we care about, okay? So to get a clean line across clean signal across a wire under those circumstances, you want to make the wire's electrical parameters uniform. If you don't make them uniform, all sorts of bad things happens along the way. You'll start getting reflections along the way, stuff like that, that will mess up your transmission of your signal. So, by the way, I don't really know anything about power, but like you can see, if you, let's say you had an AC, like our power is AC, right? You want to get from the whatever's generator to this room, you want to get 110 volt in here so we can use that current and that voltage, right, to generate lights and other things. We're basically sucking power out of that plug, right? You guys with me? So it's like as if it's like a gas station. I don't know, whatever it is. You can think of that plug as like a gas station. If they didn't deliver that voltage and current, whatever, to us using a clean transmission line, right, the length of these lines are long enough, although it's only 60 hertz, we're talking about many, many kilometers we're traveling over, that these reflections and stuff would actually like mangle our power, so we couldn't really, there wouldn't be 110 volts coming out of that line with a clean amplitude. And it'd just be all sorts of stuff reflecting and transmitting, reflecting and transmitting. And all those things would, like, sort of, as you'll see, they're kind of like going to cancel each other out. So the real power being delivered to that plug would be much, much smaller than the amount of, like, that power, obviously, you guys know, it's enough to, like, fry us. Like, it's a good amount of power, right? So, like, that's sort of, that's where transmission lines kind of started. If you want to get that in your head about a model of what people were trying to accomplish. They're trying to accomplish sending something from A to B, whether it's AC voltage, or now we're using it for information with sending bits and stuff across. We're just trying to send it across efficiently without getting a lot of loss. And what do you get? How do you get these losses, et cetera? If you don't have a clean line, you basically are going to get reflections and all sorts of other things, okay? So the way you get a clean transmission line is you make every segment look like every other segment. So if you have a transmission line that's 10 miles long or 10 centimeters long, you want every, like, micrometer or millimeter of that transmission line to be like every other millimeter. Okay, everybody with me? Okay, and so you have these types, you have these different types of transmission lines, like coax transmission lines, coplanar, we talked about different ones, but generally we can model all of them as a two-line transmission line. And all of these two-line transmission lines, you can model them, if you don't look at the losses, hopefully, again, we'll look at the losses today, you'll look at them as a bunch of L and C. Oops, that's too small for you guys, right? As a bunch of L. Is this any better? Or it's too small still? Good? Okay. L and C lines. And these inductances L and C of a transmission line, L is inductance per meter, and C is capacitance per meter, because we only want to keep track of, we're not keeping track of the total inductance and capacitance, but how much inductance and capacitance you have per, like, little bit of line, because we want uniformity, right? We want the uniformity to be the same all across the line. Because if I just gave you the capacitance of a transmission line, that whole capacitance could be at the beginning, it could be at the end, it'd be kind of meaningless. We want that number to be uniform, inductance and capacitance. Okay, and then we said, okay, well, what happens when these guys get really this distance? So this would be Z point Z. So this is, we call this the Z direction. And this is Z plus delta Z. Let's call this Z0. Okay. And then we said, okay, we came up with, like I said, a KVL. This is Kirchhoff's voltage law, Kirchhoff's current law, around one of these loops. Okay, and we came up with this equation. Where the heck is the equation? That the voltage form of which is going to be, and then we said, okay, we come up with this KVL, KCL, and then we look at delta Z goes to 0 asymptotically, so that delta Z, if delta Z becomes very small, if this distance goes to small, delta Z also becomes like dZ, okay, the derivative of Z. Okay, under those circumstances, we end up with this equation for the voltage. I really screwed this up. Sorry, guys. So, see, that was a good thing about not recording, because this is the wave equation. I had current on the other side. And then there's a current equation. Okay, and so these ended up being the equations that describe how because of this KCL, KVL, how voltage and current would go through here, and they have this solution in the form of these wave equations, which are f of t minus square root of LCZ, or f of t plus square root of LCZ. And what this says is, in general, you can have, would be like a wave traveling in the plus Z direction. And this is a wave traveling in the minus Z direction. So this, what does this tells us? This tells us that I can launch a waveform into this thing, and it'll predictably move through here as a function of distance and time. Okay, this is sort of what generally I'm saying here. Okay, and that predictability is a function of the inductance and capacitance of my transmission line, because those are the parameters that I have here.
Professor?
Yeah.
So you said this equation represents the solution of how the wave are working into like being transmitted into the transmission.
Yeah. But you could launch any kind of, this is the reason I'm keeping it general at this point, is I'm saying any, like f could be anything. But as long as inside the function it's got this form of t plus square root of LCZ or t minus square root of LCZ, it means it's traveling, like I'm going to launch it and it's going to just travel down this waveform. That's what it means. Okay, however funky, it could be a square wave, it could be a sine wave, whatever. Okay. So then, okay, so, and it turns out that because of this, the velocity of the wave is 1 over square root of LC. Okay, this is for, by the way, this is again for a lossless transmission line. Okay, so we haven't added resistance and conductance in here. I'm just gonna leave the phasor notation until we get to it before, I'm not gonna like repeat that one, but I'm repeating that one. So, well, let's think about this for a second. So velocity of the wave, okay? It's function of the L and the C, okay? And then we came up with another concept called the impedance of the transmission line. Okay, so basically, God, for the impedance, I do need to talk about the phasor notation. Okay, so why? Why? Sorry, guys. Okay. What's the best way to explain this damn phasor notation? Okay, so let's say a general form of, if you look at this guy, let's say it's some voltage, right, is V0 plus cos of omega t minus beta z. But so here, what I'm saying is, okay, so this, does everybody see how this is our wave equation solution? It's got omega t, so it's got this t component here, minus something times z. Okay? So this looks like, this is gonna look like a wave, right? Because do you guys remember how this looked like a wave? Yeah. Claire, is it good? Does it make sense? Jump in, ask the question if it doesn't make sense. Yeah, Mike.
Where did the B come from?
Well, so this is a general, so this is sort of like, it's actually beta. Right now, it's
1 over the square root of LC.
let me think about that one. So beta, the thing is we also have omega here. So think of it as a general term right now. Because beta, the definition of beta is 2 pi over lambda. But hold that thought. Just think of it as a general thing right now that decides how fast you're going. I think, is it Dan? Dan asked me this thing about beta last time, and I don't have a good answer yet.
I know looking at
About-
is omega naught times square root of LC or something like that. I can't remember that.
Yeah, it's like there's an equation for it, but what it means I'm still trying to like internalize, okay? So anyway, just for the sake of discussion right now, just think of it as this thing that's defining how you're moving in the z direction. How this cosine wave is moving in the z direction. Okay, yeah.
I don't really get, why did you get the velocity of the wave to be 1 over LC, the square root of LC?
Here? You mean?
No, I'm talking about the equation says velocity of the wave and it says 1
Ah, yeah. So this is the velocity wave. It's 1 over square root of LC. So let's talk about that for a second. So how is velocity of wave square root 1 over square root of LC? Okay. What's your name? Sorry?
Leslie?
Leslie. Thank you, Leslie. Okay. So let's think about this. So this is if you have something that's f of t square root of LCZ. right? We're claiming if we have this as a function, then the velocity of this function is 1 over square root of LC. Okay, so let's say this guy looked like this. So at time t equal to 0, it was at z equal to z0. Okay, so this is my this two lines are my transmission lines. Okay, and then at another time, it moved over here. So I'm just going to keep track of this peak. Okay, so let's say this moved over by delta z. Okay, so the velocity is delta z over delta t, right? That's velocity? That's how fast things move, is how fast did this move from here to here? Are you with me there? Okay, so when let me make sure I got this answer for you. Okay, at t is equal to delta t, z is equal to, wait, what do I want to say here? So at t equal to 0, z equal to z0, right? At t is equal to delta t, z is equal to delta t over square root of LC. Because here, f is minus square root of LC z0. Here, f is equal to delta t minus delta t over square root of LC z0. Wait, z is z is equal to what am I doing? Okay, I want to show how this guy is moving across, right? So here is t equal to 0, z equal to z0. So I got that. Here I have f of, so f moved by delta t minus z is delta t over, oh, okay, let's say this is 0. Okay, so this is f at 0. So t is equal to 0, z is equal to 0 here. Okay, so this is f of 0. So if I plug in for z here, delta square root of LC is end up f of 0 still. Let me restate that, okay, because I probably didn't do a good job here, okay? So my equation is f of t minus square root of LC z. That's my equation.
Question.
Yeah.
Does Z represent the position?
Z represents the position along the transmission line, okay? And t just represents time, okay? So if you think of the waveform at time equal to 0, so this is the z direction. Let's say this is the 0 of the z direction, okay? And this is time equal to 0. So imagine the waveform was here, the peak of the waveform was here at time equal to 0, okay? Was at z equal to 0. So here is f of 0, okay? So I want to see at what time is f of 0 over here. So this guy with time, it moves over. Like think of this as being one, so at time equal to 0, it's someplace. At time equal to 1 second, this distance has to get bigger for this to, when subtracted from 1 second, to make this 0. Does that make sense, Leslie?
Why don't you have to go to 0?
F of 0 represents where the peak is. Okay? So it just says the value of the function at, so this is a function that's a function of distance and time, right? F is a function of distance. F has got a z as a function of distance and time, okay? So a function that's a function of distance and time, it has like a value at any point. Did you see that? So if as time and distance change and that function doesn't change its value, it means that it's moving without changing its shape. Does that make sense? So does that make sense to everybody? I'm not sure what I'm saying makes sense. I can kind of like mathematically see this, but if I have t minus square root of LCZ, okay, if I have a function like this, which is this wave function, okay, as this t is increasing in value, so to keep this constant, to keep that constant, as t is ticking up in value, z is also has to tick up in value for that subtraction to just keep the same number. So I could have told you f of 1, f of 0, I could have told you f of 1, f of 2, f of 3, like anything, any number. I'm just telling you f of 0 because I'm trying to keep, it's easier to think about 0. But I'm just saying that f of 0, imagine if it's where the peak of the function is. It's just the location of the peak of the function. But it could be, you could be looking at anywhere down this function. So if you wanted to keep track of this point, we can keep track of that point, call it f of 2.5 or f of 2.9 or whatever number you like. Okay, f of 0 is just easier to say, okay, I'm going to assume at time equal to 0, I'm going to call that z equal to z0. Just because to makes my math easier. You guys with me? Okay? And then I'm going to see how this guy, because the reason why it's a wave function is a wave, imagine a wave like a wave in the ocean. It's traveling through the ocean. It doesn't change its amplitude, it's just going through, right? So this guy, and so with time, as time is ticking, if you're looking at a wave in the ocean, like at 0 seconds, it's like, it's like a 200 meters out. A second later, it's 100 meters closer to you. Half a second later, it's 50 meters closer to you. But it doesn't change its shape. Okay, the wave is just coming. So it's changing as time is ticking off, it's changing its location. So that's a general wave function. Okay, so a general wave function looks like something like this: f of t minus, let's call it some other, let's call it az. Okay, so forget about LC for a second. Okay, so it basically, why does it have this function? Why does a wave function have this function? Well, if t is ticking up, goes from 1 second to 2 seconds to 3 seconds to 4 seconds, etc., for this to have the same value, z also has to go up by a certain amount, because this sum or subtraction has to be the same. Does that make sense? So what we're saying is A represents the velocity of that wave function. And we're saying, well, why do we say that A represents the velocity? Well, if I just keep track of where f of 0, let's say the peak of the function was at f0, okay? Some time later, some delta time later, so f of delta t minus a z later, so z, this is z2, another location for z. Okay, this guy would have to represent delta z over delta t. Sorry. A would have to be 1 over delta z delta t for this guy to be also f of 0. So let's say this z2 is delta z. No? Who else is confused? Raise your hands.
I'm confused how you're saying A is the wave velocity. It's 1 divided by LC, or square root of LC. Because it's also, the velocity has nothing to do with the wave itself. It's just the transmission line you're going through that dictates your velocity.
Yeah.
Is that correct?
Yeah.
So why don't we even look at the wave right now? Why don't we just look at the transmission, just do circuit analysis on it to understand the velocity we're going through? Isn't that an easier way to look at it?
Can you say that again? Sorry.
So instead of like looking at the wave and trying to understand it through the functional line, you just look at the transmission line in a circuit element kind of analysis fashion to figure out your wave or your velocity.
Well, so the thing is, what would you do? You would have to solve a bunch of KVL and KCLs. Is that true? For every length of the transmission line. And see how you're handing over this voltage to the next batch, to the next batch, to the next batch, to the next batch. Do you see what I'm saying? Is that what you mean? Like you could just look at this solve KVL, KCL here, come up with a voltage and current here, solve KVL, KCL here, come up with a voltage here. Is that what you mean? Is that what you would do?
I guess. I mean, all you have to find is the delta between two, right? To find. Figure
But
that
this
out.
is kind of what you're doing. You're doing the delta between the two.
Yeah. So that's kind of what the velocity is.
And the way, so let's put it this way. You're finding the delta between the two, and that delta has a, has a shape of a wave function. Like, let's put it this way. Before I said that you can get a waveform going through a transmission line, we didn't know that for sure. So the first task was to sort of prove that this thing goes through the transmission line without getting distorted in a lossless transmission line. Does that make sense? Because we didn't know that, right? First task was to prove that that is the case. So in some ways, you could say I'm like proving that that's the case. If I had these sections, the solution of that is that a wave just travels through it as a function of time with a certain velocity. But like, it could have been maybe some other solution, I guess. Does that make sense, Dave? Is it Dave? Sorry, Dan.
Yeah.
Dan.
Yeah,
I'm sorry. It's a struggle. Mike, what's up?
So when you're shooting your waves throughout the transmission line,
Yeah.
how fast it goes through is determined on the quality of the transmission?
It's determined on the inductance and capacitance per unit distance that you picked for that transmission line. Okay? So that's how fast your wave is traveling through there.
And if you wanted to send it faster, you would have to either lower the inductance and capacitance.
So we're saying the velocity is, what did I say? Is 1 over square root of LC, right? So yeah, you'd have to lower the inductance and capacitance. You'd have to lower that combination. Yeah.
And
Andy.
would that like cause it to be more unstable? Because if you're trying to move it at the higher velocity at the cost of your inductance and capacitance, would that cause it to?
Well,
Is it not
No.
that you would just want to make it go faster, right?
yeah, you could just try to reduce that inductance and capacitance as much. I don't think it would cause instability. In practice, I think you have a range of geometries, like you can only make this thing so big, and like the materials that you have available to you, it could only get so, like you have only so many values to pick from.
So it's
Okay.
more of like a price and material thing rather than.
Price, pragmatic. Like imagine if your cable was, like your coax cable in lab was this big. Okay, like you'd probably use that to like do an undersea cables that, you know, would probably be okay. In fact, they're probably that big. Or, you know, when you see the power lines, these are like transmission lines, they are pretty big. So that's a reasonable thing there. But if you had those in the lab but trying to build electronics with them or put them in printed circuit boards, like you got a problem. Does that kind of make sense? Yeah, but it's that combination of inductance and capacitance. Okay, so let me put it this way. So at some point in this class, hopefully, we'll figure out how to calculate inductance and capacitance. Okay, but for that we need Maxwell's equations. We need E&M theory. So right now we're just using inductance and capacitance as if somebody calculated for you and gave it to you. And this is what you're faced with. You got a transmission line, it's got this inductance, it's got this capacitance, and so the wave will have this velocity going through. Okay? And then we'll see how to under some simple ways, you can calculate the actual inductance and capacitance, but we need electromagnetic E&M theory for that. Leslie, did I answer your question?
Can we please go back?
Or would you like to go back to here?
To the last page where you define
Here?
yes.
I think I'm doing a really bad job of this. I'm gonna try to like figure out if I can build an animation or an Excel sheet or something that I can, it's just a function of as I step, when I have time, I don't have like different ways of putting this so it's not confusing. When the reason this is a so-called wave equation, what does a wave do? A wave keeps its shape as time and distance are changing. Again, like imagine a water wave, right? It's like a wave in the ocean. It keeps its shape. As time changes, its position also changes. It's moving towards you, or maybe it's moving away from you. You're with me with that concept, Leslie? Just the concept of a wave, what it would look like. So it has both time and distance inside the function. So mathematically, if I say I have this thing that has, that as time changes, its position changes, but it keeps its shape, it needs to be both a function of time and distance. That's why this is a very general, what we call this a wave equation, because it's a general term. And if it has to be, if it was time times distance, or time divided by distance, or something like that, it wouldn't work out as something that wouldn't change its shape. But if it's some time, something times time, plus or minus something times distance, right? As time changes and distance changes, this function keeps its shape. So it's a general solution to a wave traveling in time and space. And because of that, this ends up being 1 over the velocity as it's taken away. Yeah. Okay. All right, guys. Let's see. Okay. So, where was I? We're talking about the phasor notation. God, Leslie almost saved me. Okay. So, in general, this voltage has a function of V, something that goes in the positive direction and something that goes in the negative direction, okay, in a transmission line. So that is equal to that plus V0 minus cos of omega t plus beta z. Okay, so this is like a cosine wave that's moving in the positive direction with amplitude V0 plus and moving in the negative direction with amplitude V0 minus. Okay? So again, to make calculations simple, okay, we're going to assume for a second that omega is constant. So I'm going to look at just one frequency wave. So if I assume that's the case, okay, this guy, well, is basically ends up being V0 plus e to the omega t times e to the minus j beta z. I can get this cosine kind of in this form. I can write the cosine in this form. And if I assume again, this is just for the sake of analysis, if I assume the frequency is constant, I'm going to call this a phasor. And I'm going to just call that like V0 hat. So I'm just not going to worry about this for now. So I'm going to ignore this for now and just worry about that. Okay, and I'm going to do my analysis in this phasor notation, and then once I'm done with my analysis, I'm going to come back and add those things in. You guys with me with this phasor notation?
I have a question.
Yeah.
Based on the discussion we had when we were trying to explain why we use imaginary stuff, you said the imaginary value, that's what like helped us determine. Oh no, that was position in time. Was it the phase or was it the position?
Yeah, it's like a phase of the waveform. So your question is, why does the phase relate to velocity and time and position, or what's your question?
No, my question is, I thought the imaginary one, the one with J, would be the phasor.
It is the phase, not the phase. So there's a phasor, which is a word that just means that. And then there's the phase.
Okay.
So those are like kind of two separate things, sorry. Yeah. I didn't make these things up. Somebody did though. You guys with me? So phasors are just something we're using in notation. Okay? Boy, everybody looks,
These
even.
phases just E negative J beta T Z. That's the phase, technically, right?
That's the phase.
That's the phase, and then
That's the
phasor is just
phasor.
like the magnitude.
Yeah, phasor is what sort of comes with the phase. Yes, Claire.
Do these phasors have anything to do with the phasors from circuit analysis, or are they just a different notation altogether?
I don't remember the phasors from circuit analysis. Can you remind me what those were?
Notation's different. We don't usually, we do like magnitude and then you just do an angle sign and then write in degrees, but this one we have it.
So it'd be magnitude and
It's-
phase,
it's
but it
the
was actually a
same.
phasor.
It's a phasor, but the notation's slightly different.
Ah.
But it is the same thing.
I
Just
see.
don't do negative J beta Z. Because
Okay.
it's not really useful when you're only doing one phase,
I see.
like a sine wave.
And this is, you guys
That's why you
see,
use this notation in signals
Yeah.
and systems, because you got multiple frequencies.
yeah,
Because I'm assuming once you do this and it's not omega constant, there's a bunch of different frequencies, you gotta add them all up.
yeah, gotta add them all. Yeah. Did you use the phasor stuff in power, or where did you guys use it? Or any circuit analysis? In power?
But yeah, like I
Ah.
said, you use a different notation.
Mm,
Like
okay.
magnitude.
Yeah. Is that Claire? Sorry, is that a reasonable answer? Okay, awesome. So why did I mention these bloody phasors? Because we have to use them, but also, so we have this concept that the velocity is 1 over square root of LC. Okay? And then we came up with this concept of the characteristic impedance of a, so what are we trying to do, guys? We are trying to model this transmission line so we can use it. Okay? With a few things. So I'm saying one of the things we need is how fast stuff goes through there. The other thing we need to do is figure out this characteristic impedance of the transmission line. And so call that Z0. This is not distance, sorry. Maybe for this Z, I just won't put the dash. So Z is distance along T line defined, and then I'm gonna try hard not to put the dash. I don't know why they have all these Z's running around, but they do. Is impedance. Okay, and Z0 is so-called characteristic impedance of the transmission line. Okay, and so generally, okay, so what do we know right now? We have this waveform. We broke down the waveform into a phasor format, okay? And there's a voltage waveform and a current waveform. Everybody agree with that? A voltage waveform and a current waveform going in the plus direction, and potentially a voltage and current waveform going in the opposite direction. So the Z naught, whoops, I did it. Z naught is defined as the ratio of the voltage phasor going in the positive direction versus the current phasor going in a positive direction. Or you pick it, Z, again, I'm trying to keep these separate. Z0 is voltage phasor going in the opposite, in the negative direction, versus the current going in the negative direction, so it should be negative. That's a characteristic impedance. And so impedance gives you the ratio of voltage to current, okay? And why is it called characteristic? Is because for every segment of that transmission line, you have the same impedance. And as long as you have an L and a C, the L and the C define the behavior of the transmission line, okay? And the Z basically ends up being, the Z naught is square root of L over C. Okay? Yeah, Andy.
So basically, the V0 over I0 is like what it is, but then the square root of L over C, that's like what we'll get for it? Yes.
Square root of L over C gives you the relationship between the voltage and the current
Okay.
at any point. Okay, and it ends up being, so basically, I'm gonna make a claim that if I have a two-wire transmission line, this is where we kind of stopped. If we have a two-wire transmission line, all I need to sort of describe the behavior of that, or this characteristic impedance Z naught, which is square root of L over C. Okay, and I need the velocity of that line, which is 1 over square root of LC. Yeah.
I have a question for
Yeah.
characteristic impedance. Why isn't there no J or something? Because right now we're saying it's a real value.
Yeah.
And it's an imaginary area because it's capacitance and inductance. And since we're saying there's no losses, there's no R there right now.
Okay.
So why is there no J in the equation for the characteristic impedance?
Why isn't there a J? Why is it real?
Why is it real? Yeah, why is it a real value, not an imaginary value?
Why is it a real value? What? Well, mathematically, hold that thought, because we'll talk about that in. So what happens is the real enigma of this thing, which is probably was going to be your next question. I don't know, maybe it was or wasn't. But if something is real, if an impedance is real, that's a resistance, right? Everybody with me? If a purely real impedance is resistance, and we're calling this a lossless transmission line, right? I had the temerity to call this a lossless transmission line. But if you have resistance is you drop power across a resistor. A resistor dissipates power, right? So how can this be real and be lossless and be made out of inductance and capacitance and be real? So that's the question you're really asking, which is where should I put it? Well, it's something to ponder, huh?
It's an engineering feat.
It's an engineering feat, but also something to think about, because it is a what's the word for it? I don't know if it's not it's a something that doesn't quite make sense. I'll talk about like how you can think about it, but there's actually a whole section talking about what that is. Okay, I can tell you just mathematically, if you have, you have J in the inductance, and you have J in the capacitance, so they cancel each other out mathematically. Okay, so you end up with like a real number. You don't end up with a J here, because the inductance and the capacitance sort of like deal with each other, and you don't end up with like a negative number underneath this either to get a complex value. Okay, so if mathematically you end up with Z not being real, the question is, if it's real, how come it's lossless? Yeah. Okay, good question. We're gonna spend a bunch of time on that. Okay, so if I have a transmission line made out of these inductors and capacitors, it'll have some characteristic impedance and some the waveforms are going to go in some velocity. Okay? All right, so that's where we kind of were at the end of the class. Okay? So if this was an infinitely long transmission line, okay, that's all I would need to know. So I would just sort of shoot waveforms into this, and these would go, if I'm shooting them in the positive Z direction, they would travel there so whatever waveform I put in the input for the voltage, it would just go out to infinity, and the relationship between the voltage and the current would be defined by the characteristic impedance of this line, okay? And the speed at which it would go to infinity would also be defined by the velocity of this transmission line, okay? So I'm just gonna shoot it, and I'll just keep going. So that's a lossless kind of infinite transmission line. And nothing would come back, right? I'm just shooting stuff. There's no reason there'd be a waveform coming back. I'm just shooting stuff forward, and I'm just going to keep going. Or I can shoot stuff that way, if it's an infinite transmission line, lossless. I'm just going to go shoot that way, and there'll be the same characteristic impedance, would give you the ratio of the voltage to current at any point in this transmission line, and the same velocity would tell you how fast you're going in that direction. Okay? That's all I would need to know. That's what would happen. Okay? So, okay, fine. But most transmission lines are not infinite in length. In fact, none of them are, because we don't have anything that's infinite in length. So the next part of where I think we kind of stopped is what happens at the end of this transmission line. So if you had an infinite transmission line, this is all we would need to know. But given that there is an end to transmission lines, we also need to figure out what happens at the end, okay? So what happens at the end is that you have, at some point, you have some kind of a load hanging off. There's some termination. There's some end to this transmission line. And that'll have some, some impedance, Let me call that Z sub L. So Z sub L is defined as the load impedance. So I have Z sub 0 and Z sub load. So this is the characteristic impedance. And this load impedance is not a transmission line now. It's just kind of a lumped thing. Okay? So like if you had in the lab, your transmission line would be your coaxial cable and your load would be your oscilloscope. And that oscilloscope has some kind of input impedance, like a mega ohm or 50 ohm or something, but it's like a lumped entity at the end there. Okay? So, and it turns out that, so you have, some current going into your load. Okay, so you have some current waveform. Some voltage waveform is going this way. Okay, I launched some voltage waveform this way, right? And it has, that voltage waveform has a current waveform associated with it. That association is given with the characteristic impedance. So you guys see that? I have some voltage and current waveform going towards my load. Okay, when it hits the load, okay, just think of the current when it hits the load. Depending on the value of the load impedance, that voltage, so the voltage at this point will be whatever the voltage was of my waveform. You guys with me? So this voltage waveform is coming here, hits this point. Okay? At that point, that voltage across the load, given the impedance of this guy, it has a certain current going into that load. You guys with me? You agree? Okay? But there was a different current coming with the voltage while it was with the transmission line. So this voltage, whatever my voltage is, gives me a certain current for the Z0 and a different component, the current for the Z sub L. As long as Z sub L is not equal to Z0, that same voltage here gives me a different current into this than the current coming in. You guys with me? No? Yeah? No? So Z0, so think of this, or voltage phasor here. Whatever voltage, just think of it as a voltage. Okay? So this voltage has a current at this point. There's a current I0 associated with this voltage, which is is it Z0 over V0? No, what am I doing? Yeah. No, it's V0 over Z0. Sorry, guys. You with me, Leslie? That was kind of our definition of the characteristic impedance. Okay, so that'll be the current coming in here associated with this voltage. Okay, but just at this point, just along this line, when I hit this guy, I'll put the same voltage, V0 plus, across the ZL. You see that voltage is simultaneously across the transmission line and across the impedance, the load impedance. You're with me? So there's a current I0 plus here, and there's a current IL plus, which is the same V0 hat over ZL. So I have a voltage across this load, and there's a current that wants to see a certain current, and there's a voltage and current associated with the transmission line. The voltage is the same, but those two currents may be different. right? Depending on ZL and Z0. Everybody with me? Okay? So if ZL is equal to Z0, if ZL is equal to Z0, then those two currents are the same. Okay? If they are not the same value, if Z sub L is not equal to Z0, you got some delta current. So some current's going in, not that all that current is getting pulled in. So you have some extra current, right? So what happens to that extra current? That current goes back into the transmission line going into the opposite direction. Okay? And that gives way to the reflected wave in a transmission line. So you got this waveform happily going through the transmission line like as a wave, nothing's changing with it. Each point in this waveform has a voltage and a current associated with it. It hits the end of the transmission line, okay? If the end of that transmission line does not have the exact same relationship between voltage and current, meaning the exact same impedance as the characteristic impedance of the line, I'll get some current and therefore some voltage reflected back into the line. You guys see that? Because there's no place else for that it's this extra current to go. There's no place for the current to go. Yeah.
Why can't ZL be lower than ZL?
How can it be?
Why can't it be lower, a lower impedance? Because then it'd just make it easier for the current to flow through it, wouldn't it? But
It
then
would be,
voltage-
as long as there's a difference, you're gonna have a difference in current to deal with it. So like because of Kirchhoff's current law, right? So it just depends on, is it a positive going current in terms of, will you get a, if you think of it as in terms of voltage, because usually you look at voltage, right? Will you have a positive going voltage spike or a negative going voltage spike? In either case, you'll get a spike, and in either case, you'll get that reflected back into your transmission line.
So if the
But-
impedance is higher, it's gonna have a positive spike, and if it's lower, it's gonna be a negative voltage spike.
I'll have to think about that, but yeah, something like that. But either way, this difference in current is gonna get put into it'll have either a positive sign or a negative sign in terms of the amplitude, but the direction of it is gonna be going in the opposite direction. That's the only place it has to go. Because the transmission line ended, right? There's no, at the moment, we're assuming nothing came later, right? So you have a current going into this load, that's the end of this transmission line. If that load current is different than this load current, that current has to go somewhere. That difference in current, whether it's more or less. The only place it has to go is back into the transmission line. Does that make sense, Daniel?
Yeah.
Because it has to go somewhere. It's not gonna,
I was just thinking because you'd have a lower impedance on it, it would
Yeah.
wanna flow through the lower impedance line, but I guess, I don't know, the reflection.
well, I think it is gonna like it's gonna go down. The voltage is gonna go down. So let's say if it goes through, right, what happens is like your voltage, like you can't source enough current from your transmission line to keep the volt. You're trying to keep the voltage the same at this transmission line, right? So if your load is trying to pull more current, then the transmission line can source. You can think of this voltage as collapsing, which means something is changed in your transmission line equation, which means you can think of that voltage collapsing as if you had another voltage waveform going in the opposite direction enough for that collapse. Does that make sense?
Not really, but like, kind of at the same time. I can't really visualize it because you're saying voltage collapse, but I'm like, what does that really mean? Is it because there's a reflection that's dropping the voltage down, or what is it
Yeah.
look like graphically?
Yeah.
That-
Yeah.
Is this the oscillation or something?
So think of it this way, is if you had, you can. Graphically, what does it mean? So think of that very end point in the transmission line. Okay, the very end of your transmission line. Think of it as that. So it was like sort of, this was minus infinity and this was the load. Okay, so this, I'm not even gonna do the phasor notation for a second. Imagine this is some voltage. Okay? And there's some current coming in, some voltage, some current, but I'm just gonna worry about this particular voltage here. Okay? And there's some current I sub L here going here for the same voltage. So this has gotta be some, so this is some Z0. So if this current is less than this current, what has to happen? So where does that current go? Or where does it come from?
It's gonna come from the transmission line, it's gonna try to suck in more current.
The transmission line is trying to source more current in here,
Yeah.
right? But there's no current to source. That current came traveling with some wave. There's no, your voltage source that sources current is like 1,000,000 miles over here. It doesn't even know, it doesn't even see what's going on here. Some current traveled with this voltage, some current wave traveled with this voltage
Is this because
wave.
it's like also, there's that delay factor, so saying we're at this peak here or there, but when it hits that load, we're like somewhere here on the sine wave, so it's drawing less current at that point or something? Because there's less voltage going to the load at that point.
At this point, if I draw that point with time, yeah, you're gonna have all sorts of like variations,
That's what I'm
right?
saying, so like it's, let's say that point, it's at the peak, but during when it's hitting the load, it's somewhere like
But-
lower in the sine wave or something?
No,
That's
no,
what
no,
I'm trying
at
to say.
any, so we're saying at given a point in time, okay? So remember, we pulled out omega t out of the phasor notation, so we pulled time out of the phasor notation. So right now, we're not even thinking about time. At the same point in time here, whatever that voltage, you could pick this point in time or this point in time.
And it's at both points, it's at the load and at that point.
Yeah,
Okay.
at that point, you're both, at that point in time, both the load and the transmission line see the same voltage at this point in space. Okay, a time later, they'll see a different voltage, but they'll both see the same different voltage.
Because that's
see
what
what
I
I'm
thought it was, is the delay factor that was causing the current to be different, I guess. I don't know, because maybe I'm thinking about it
No.
like a normal circuit, and it's clearly not the case.
Yeah, so imagine if you had, so I think the thing to think about is that if you have I guess it is a normal, think of it as a normal circuit, okay? So if I have, so think about the Kirchhoff's current law here.
That's what I'm saying, it's a series though, shouldn't they have the same current? IL should be the same for both, but you're saying it's different if we're thinking as a normal circuit.
Well, okay, think of it as being the same current, right? So this guy has some current going in here. Okay, what I'm saying is, the load wants to pull in some current. Okay? Any difference means like, I guess you can think of as the load just injected another current, delta current, back in, going in the opposite direction.